Hello, I am Denise, one of the presenters of the Enlightenment project. We are pleased that you have decided to join us on this extraordinary journey through enlightenment. In today's video, part 2 of quantum theory, by the way. It's one of the most fascinating wonders of creation. We will be exploring tunneling and covering how it affects our daily lives with technology, and we invite you to sit back, relax, and enjoy the journey.
Imagine throwing a tennis ball at a solid brick wall. You wind up, put all your force into the throw, and watch as the ball hurtles towards its target. In our everyday experience, it always bounces back. The wall is an impenetrable barrier. The ball simply doesn't have enough energy to break through. It's a straightforward interaction governed by classical physics. But now, let's shrink down to the quantum world, where the rules are very different. Here, a particle like an electron, faced with a similar barrier, can simply appear on the other side as if by magic. It defies our intuitive understanding of how the world should work. It's as if the electron has tunneled through the wall. This is quantum tunneling, one of the most bizarre and fascinating phenomena in quantum mechanics. It describes particles passing through barriers they shouldn't be able to cross, according to classical physics. These barriers could be energy fields, physical obstacles, or anything that would normally prevent a particle from passing through. It's a direct result of the wave-like nature of matter, the principle that particles can behave as both particles and waves. This duality is key to understanding tunneling. Instead of existing as fixed points with definite locations, particles exist as clouds of probability described by a wave function. This wave function tells us the likelihood of finding the particle at any given point in space. Sometimes a bit of that probability leaks through a barrier, even if the particle doesn't have enough energy to overcome it classically. This leakage allows the particle to tunnel across, appearing on the other side as if the barrier wasn't even there. It's not that the particle is physically boring through the barrier, but rather that its probability wave extends to the other side. This isn't just theory. Quantum tunneling is a real, measurable phenomenon that has been observed in countless experiments. In fact, it powers the sun. Protons in the sun's core, which are positively charged and repel each other, fuse together to form helium through nuclear fusion. This process is only possible because they can tunnel through their mutual repulsion, igniting nuclear fusion and releasing the energy that sustains life on Earth. Without tunneling, the sun would simply not shine. Radioactive decay, the process by which unstable atomic nuclei lose energy and particles, also relies on tunneling. Alpha particles, which are composed of 2 protons and 2 neutrons, escape atomic nuclei not by brute force, overcoming the strong nuclear force that binds them. Instead, they do so by slipping through quantum barriers, tunneling their way out of the nucleus. These processes are fundamentally random, meaning we can't predict exactly when a specific particle will tunnel. Yet, on a large scale, with many particles, the rates of these processes are predictable and governed by precise quantum rules at work. It's a statistical certainty arising from the probabilistic nature of quantum mechanics. Beyond these examples, quantum tunneling is essential for life, playing a role in enzyme catalysis and DNA mutation. It's also crucial for modern technology, enabling the operation of transistors, solar panels, and many other devices that power our world with clean energy and ultimately shaping the universe as we know it. It's a powerful reminder that the quantum world, though seemingly bizarre and counterintuitive, is far stranger and more fundamental than our everyday experience. So, the next time you bask in the warmth of sunlight or hear about radioactivity, remember, it's quantum tunneling in action, working tirelessly at the subatomic level. The universe's most basic rules are not just odd, they're essential, underpinning the very fabric of reality. Without tunneling, stars wouldn't shine, providing the energy for life, and atoms wouldn't decay, releasing the elements that make up our world. The quantum world is not just weird, it's the engine of reality, driving the processes that shape our universe. Our existence depends on particles doing the impossible, defying classical physics, every moment of every day. That's the magic and the power of quantum tunneling, a testament to the strangeness and beauty of the quantum realm. The device you're using right now runs on quantum mechanics. At the heart of every computer and smartphone are billions of transistors, tiny switches that rely on quantum effects to work. Electrons in these transistors don't flow like water, they jump between energy levels controlled by quantum rules. Engineers design these microscopic circuits by harnessing the strange behavior of electrons in semiconductors. Without quantum theory, the digital revolution would be impossible. Every message, video, and search is powered by quantum physics. The quantum world isn't abstract, it's in your pocket, shaping your life. Our mastery of quantum mechanics has transformed society in just decades. The digital age is the story of quantum made real. Lasers, ubiquitous in modern life, they're used in everything from supermarket scanners, where they swiftly read barcodes to keep the checkout lines moving efficiently, to incredibly precise eye surgery, correcting vision with beams of light, a testament to the power and control we've achieved over light itself. These lasers, seemingly simple tools, are actually a profound application of pure quantum technology. They work by stimulating atoms, energized particles, to emit identical photons, those fundamental units of light. This coordinated emission creates a powerful, highly focused beam of light capable of cutting through steel or delicately reshaping the human cornea. This process, called stimulated emission, was predicted by Einstein decades before lasers were even invented, and it relies fundamentally on quantum energy states, the discrete levels that electrons can occupy within an atom. GPS, the technology that guides us through unfamiliar streets, also depends critically on quantum physics. Satellites orbiting high above the Earth use atomic clocks, incredibly precise timekeepers. These clocks keep time by measuring the incredibly stable and precise frequency of quantum transitions, the jumps electrons make between energy levels. These transitions occur within atoms, providing a natural, unvarying standard for time measurement. These clocks are so extraordinarily accurate that they would lose less than a single second over the entire lifespan of the universe, a testament to the precision of quantum mechanics. The location services on your phone, guiding you to your destination, rely directly on this quantum precision. Without these quantum leaps in atoms, providing the stable timekeeping necessary for accurate GPS, we'd be lost, literally wandering without direction. Lasers and GPS are just two examples of the everyday miracles made possible by quantum mechanics, technologies we often take for granted. The quantum world isn't just a realm of strange and counterintuitive phenomena, it's also deeply practical, underpinning much of the technology we rely on. Our modern world, in countless ways, runs on quantum action, a testament to the power of understanding and harnessing the fundamental laws of nature. Quantum mechanics, a realm of physics that once seemed purely theoretical, now powers medical marvels like MRI. It's a testament to how understanding the smallest parts of our universe can lead to groundbreaking advancements in healthcare. MRI scans, a cornerstone of modern diagnostics, use the quantum property of spin, a fundamental characteristic of atomic particles. This spin is particularly important in hydrogen atoms, abundant in the human body, making them ideal for MRI imaging. By manipulating and detecting the behavior of these hydrogen atoms, MRI creates incredibly detailed images of our bodies, revealing structures and anomalies with remarkable clarity. And the best part? It does all this without harmful radiation, making it a safe and invaluable tool for doctors and patients alike. During an MRI, protons in your body, normally randomly oriented, align with a powerful magnetic field, like tiny compass needles pointing in the same direction. Radio waves are then used to momentarily flip these protons to a higher energy state, a process governed by quantum mechanics. As these protons relax back to their original alignment, they emit signals that are detected by the MRI machine, revealing your internal structure with incredible precision. But quantum mechanics isn't just revolutionizing medicine, it's also transforming how we generate energy. Solar panels are another quantum triumph, harnessing the power of the sun in a way that was once unimaginable. At the heart of solar energy is the photoelectric effect, where photons from sunlight knock electrons free from atoms within the solar panel material. This process occurs within a solar cell, generating electricity that we can then use to power our homes and businesses. It's a direct conversion of light into electricity. One photon, one electron, a fundamental quantum event. The efficiency of solar panels, and therefore their ability to provide clean energy, depends critically on how well they convert these quantum interactions into usable power, a field of ongoing research and innovation. By optimizing these quantum processes, quantum mechanics is helping us build a cleaner, healthier future for all. From seeing inside the body with unprecedented detail to powering our cities with the energy of the sun, quantum rules are not just theoretical concepts. They are the foundation of technologies that are rapidly transforming our world and shaping our daily lives everywhere. The future of medicine and energy, driven by quantum innovation, is brimming with possibilities. Harnessing the quantum world is not just a scientific endeavor, it's changing how we live, work, and interact with the world around us, promising a future filled with groundbreaking advancements. Classical computers are powerful, but quantum computers promise a revolution. Instead of bits, just 0 or 1, quantum computers use qubits, which can be 0, 1, or both at once thanks to superposition. This lets them process vast possibilities simultaneously. Entanglement links qubits, allowing instant connections across distance. Quantum computers could solve problems in seconds that would take classical computers millennia. We're still in the early days, but the potential is enormous. Scientists are learning to control and protect delicate quantum states. The quantum realm is becoming our ultimate tool. Soon, we may solve mysteries and create technologies we can barely imagine. The future of computing is quantum, and our journey into the quantum cosmos is just beginning. So stay tuned for part 3 of this mini 3-part series in quantum. Follow, like, and subscribe to the Enlightenment Project for more enlightened content.